Okay, let's talk about DeMorgan's laws and unions and intersections of open and closed sets. So the first thing, let's just look by an example of DeMorgan's laws. So A union B complement, that's A complement intersect B complement. This is one of DeMorgan's laws on just two sets. So let's look at the Venn diagrams. So if I look at A union B complement, so here's A union B, if this is A and this is B. A union B complement is the stuff that's not red, right? So we'll color the stuff that's not red, let's color it blue. All of this stuff is what the left-hand side is. Right? Let's draw another Venn diagram for the right-hand side. It's the intersection of A complement and B complement. So here's A and here's B. Let's color A complement in green, dark green. A complement in dark green is all of this stuff that's not in A. B complement in purple is all of the stuff that's not in B, right? So that's all that stuff. And the intersection is the stuff that's colored both colors. So let's go in yellow. The stuff that's not colored both colors, well, this stuff is only colored purple. This stuff is only colored green. The stuff in that intersection, it's not colored at all. So the stuff that's colored both colors is the stuff outside here, which is exactly what we have got written down there. It's the same blue stuff, right? The blue stuff and the yellow stuff are exactly the same. So that's DeMorgan's laws. The picture is kind of nice to help us see what's going on, but let's actually prove what's happening here. So the theorem. Let E sub alpha be a collection of sets indexed alpha in A. A can be finite, A can be infinite, A can be uncountable. No matter what A is, we're just going to index them by A. Then the statement is, so it's just any collection of sets. If I take A and I union all of these things together and then take the complement, that's the same thing as intersecting A and A, E sub A complement. So the complement of a union is the intersection of the complements. And there's a quick corollary to this, which is the opposite statement. The complement of an intersection is the union of the complements. So a corollary is, it's not, well, it's like a theorem where you prove it, only it comes sort of directly after the proof. You look at just a slightly different case of the theorem, and that's where you get the corollary. So the complement of an intersection is the union of the complements. So we'll write that down as a corollary after we do the proof of this theorem. Okay. So let's prove this right here. So I need to start out with a collection. I need to show that to show two sets are equal, we show that they're contained in each other. Okay, so our proof to show two sets are equal, we need to show they are contained in each other. Okay, so if you show that two things contain each other, well, they sort of have to be equal. If everything in the left-hand side is inside the right-hand side, that means the left-hand side is smaller than the right-hand side or equal to it. And if the right-hand side is contained in the left-hand side, the right-hand side is smaller than or equal to it. So you must have equality. So we'll first start showing with the left-hand side is contained in or equal to the right-hand side. Okay, so let's look at what this says again. The left-hand side was the union of alpha and A E sub alpha complement, right? We want to show that that's contained in the intersection of alpha in A E sub alpha complement. Okay, so what we have to do is we have to take an element from the left hand side. So we're going to let x be in the left hand side, the union of alpha in A E sub alpha complement. Okay, this means x is not in the union of E sub alpha, alpha in A, right? For it to be in the complement, the only way it's in the complement is if it's not in the union of all of those things. So x is not in E sub alpha for every alpha. Because to be in the union, you just have to be in one of them. If you're not in any of them, you're not in the union, right? If you're not in the union, you're not in any of them. So this statement goes to here. So x is not in E sub alpha for every alpha in A, meaning x is in E sub alpha complement for every alpha in A. So since it's in the complement for every alpha, x is in the intersection of the complements for every alpha in A, which is equal to the right hand side. Okay, so x in the left hand side implies that x is in the right hand side. We've shown containment. The left-hand side is contained in the right-hand side. If we've taken an arbitrary element from over here and we've shown that it's over here as well, that means everything on the left is in on the right, so we've got this set containment here. So we're halfway there. Now we have to show the other direction. So now let's take the right-hand side and show it's contained in the left-hand side. Okay, so we're going to take an element, an arbitrary element of the right-hand side, and the right-hand side is the intersection of E sub alpha complement. Okay, so this means x is in E sub alpha complement for every alpha, right? If it's going to be in the intersection of all of the alphas, E sub alphas, it has to be in every single one of them. So x is in the complement for every single one. making x not in E sub alpha for every alpha. Okay. And since it's not in E sub alpha for every alpha, it's not going to be in the union of all of the alphas. So x is not in the union of the E sub alphas. i.e., x is in the complement of the unions. And that's the left-hand side. So we started with x is in the right-hand side this time, and that implied that x is in the left-hand side, making the right-hand side a subset of the left-hand side together. Then, with the left-hand side being a subset of the right-hand side, we get the sides are equal. And that's our proof of DeMorgan's laws. These are known as DeMorgan's laws. I don't know if I said that, but that theorem, this is DeMorgan's laws. It's used in probability quite a bit. So to measure the probability of something not happening or a bunch of things not happening, you can take, right, you can use DeMorgan's laws to calculate those probabilities. But we're going to use that with topology here and show that open sets and closed sets and the like are the same. So an exercise for you, I want you to prove that the intersection of E sub alpha, alpha and A complement is equal to the union alpha and A E sub alpha complement, right? So this was the other half, the corollary that I said you should look at. So why don't you guys do that as an exercise, and we'll move on to the next thing. Okay. So let's talk about open sets. So a set is going to be open if every point inside that set, there's like a little circle we can draw around it, right? Okay. Open sets are open if every point in the set has some neighborhood that's also contained in the set. Right. So if I've got this open set, I draw a point there, there's some radius, this is going to be some neighborhood around X with radius R, and our X is contained in E. If that's true for every point in there, I can find some radius, then the set's going to be open. Okay. Our next theorem, X is, let's say E. E is open if and only if E complement is closed. let's recall what closed meant. Closed was every limit point of the set is contained in the set. So we have to go from every point in the set has a little circle around it that is contained in there to every limit point is in the set. And this is something that goes in both directions. So let's first go from the closed set to the open set. If E complement is closed, then every point that is a limit point of E complement is contained in E complement. Okay, so if I look at something that's not in E complement, it's definitely not a limit point. So this means if X is in E, which is everything that's not in E complement, then X is not one of the limit points of E complement, right? So there exists some neighborhood of X that doesn't intersect E complement, right? This neighborhood then is entirely in E. If it doesn't intersect the complement, it has to live completely in E, making X an interior point of E. Remember, interior points were ones that we could find a little circle around? Okay. So, as X was arbitrary in E, every point in E is an interior point, making E open. Okay, so if it's the complement of a closed set, it's going to be open, because if it's a closed set, it contains all of its limit points. If you look at something outside there, it can't be a limit point, so I can draw a circle around it that avoids the set E complement. That circle shows that it's a interior point of E, making E open. The other direction, if E is open, let X be in E complement. Let's say we have a limit point of E complement. Okay, that means every neighborhood of E complement intersects E complement. So every neighborhood intersects E complement. Thus, no neighborhood of X is contained entirely in E. So X is not an interior point of E, as E is open. All points in E are interior points. So X is not a point in E. It must be in E complement, making E complement closed, as it contains all of its limit points. Okay, so as a corollary, if E is closed, E complement is open. Right, they're kind of opposites of each other. I can just switch out in this theorem E and E complement. So in this theorem, if I replace E with E complement and E complement with E, that doesn't change anything in the statement. I've just replaced a set with its complement, and that gives us the corollary. Okay. The last theorem that we want to prove today has a couple parts. And this is really where topology really comes from. It's, if I take a union of open sets, I get another open set. If I take the intersection of closed sets, I get a closed set. If I take a finite intersection of open sets, it stays open. If I take a finite intersection of closed, or finite union of closed sets, it stays closed. Okay, so lots of open sets stay open, and that sort of thing. So A, for E sub alpha, alpha in A, if E alpha is open for all alpha, then the union alpha in A of all of them is open for E alpha, alpha in, let's go with C alpha, alpha in A. If C alpha is closed for all alpha, then the intersection of C alpha, alpha in A, is also closed. And then C, if we just take a finite number of them, let's take G1, G2, and Gn, are open, then the intersection of G1 of the GIs from I equals 1 to n is open. And lastly, if we'll go with C's again, C1, C2, Cn are closed, then the union from I equals 1 to n of Ci is closed. Okay. So any collection of open sets in a union stays open. Any collection of closed sets in an intersection stays closed. A finite collection of open sets in an intersection stays open. A finite collection of closed sets in a union stays closed. All right. There are counterexamples to all of the contrapositives of these. So if a union is open, it doesn't necessarily mean each of the things in the union are open. If an intersection is closed, it doesn't necessarily mean all of the things in the intersection are closed. Okay? If I have an infinite number of open sets and I take their intersection might not necessarily stay open. If I take an infinite number of closed sets, the union of the infinite collection of closed sets might not necessarily stay closed. Okay. So let's prove these real quick, and then in the next video we'll see some examples. So let's proof of A. Let E sub alpha be open for all alpha in A. Then each x in the union of the E sub alphas belongs to some E sub alpha star, some special E sub alpha. In that E sub alpha star, there is a neighborhood that contains x. Since that neighborhood is in E sub alpha star, it is also a subset of the union of the E sub alphas, making x in the interior of the union. So, i.e., every point in the union is an interior point, and the union is thus open. Okay, so that's A. For B, we'll use DeMorgan's laws and A to show that B is true. So, if we called them C's, C sub alpha is closed for all alpha, we have C sub alpha complement is open. So the union of C sub alpha complement by A is open. And the complement here is equal to the intersection of the complements is closed, which is what we wanted to show. So there's B. For C, let's look at this. So if C, E sub I, E sub 1, E sub n are all open, and X is in the interior, or is in the intersection of the E sub i's, then X is in E sub 1, X is in E sub 2, and so on. X is in E sub n. So there are radius 1, radius 2, radius n, such that the neighborhood of radius 1 about X is contained in E sub 1. The neighborhood of radius 2 about X is contained in E sub 2, and so on. The neighborhood of radius n around X is contained in E sub n. Okay, so I've got a bunch of different small circles centered at X. I'm just going to take the smallest of them. Take the smallest. Say R is equal to the minimum of R1 up through Rn. Then the neighborhood of radius R around X is in each of the E sub i's. So it is in the intersection of the E sub i's. Right? If it's in each of the E sub i's, then it's going to be in the intersection of each of them, making X an interior point of the intersection of the E sub i's from I equals 1 up to n. And so each point is an interior point and so the intersection is open. And then D, use DeMorgan's laws again. On C. Okay, we'll see some examples next time and do some more topology